recording. Okay. Pen work? Pen works. Let's go to our notes. All right. We have to talk about linear independence and span. Did everybody watch this video?
Yeah.
Does span make sense? The span is the set of all possible linear combinations of a set of vectors. Doesn't matter whether they're linearly independent or linearly dependent. It doesn't matter how many of them are. We're just going to take all possible linear combinations. But you noticed that if two vectors were on the same line, their span was just the line. Right? You saw that in the video. You saw the picture of that. And if you have 5 vectors, but 3 of them are on the same plane as the first 2, correct? Then the span is only going to be 2-dimensional. So how do we describe vectors that are pointing new directions from ones that are still on the span of some of the earlier ones, right? And the definition for that is linearly independent. Remember that a subspace is a set of vectors that's closed under linear combinations. So what we're really talking about are spans, right? Every subspace is the span of a few vectors, and the span of any set of vectors gives us a subspace. That's what we were describing the entire time. Okay. For example, the basis I hat and j hat in R2 and the basis I hat, j hat, and k hat in R3. And if we have more than 3, rather than keep using letters, we're going to use subscripts. And we have the elementary or canonical basis vectors, E1 to En for Rn. And those vectors are the ones that have zeros everywhere except 1 in the jth spot. And that's the elementary basis vector Ej. And these elementary basis vectors are also called canonical or standard basis vectors. So R2 is the span of I hat and j hat, right? It's canonical basis. And R3 is the span of I hat, j hat, and k hat. It's canonical basis. E1, E2, and E3. And the span of these 4 vectors in R4, E1, E2, E3, and E4 is all of R4. Okay? Okay, so we have a vector with coordinates 1, 3, 2, 0. How can we represent the vector as a linear combination of standard basis vectors? Well, it's E1 plus 3E2 plus 2E3, right? And no E4s. Now, this video is not required for anybody. Did anybody watch it? No? Okay. The thing is, I found this out in 2008 when I discovered the OpenCourseWare had a linear algebra class. He and I teach this class really similar. We used to teach it identically, but I've since incorporated the 3 blue, 1 brown videos. And the biggest difference you're going to see between the two of us is he does not put definitions or formulas on the board. He'll say, well, you saw that in the textbook. I don't have to put that on the board. Right? Whereas we will take time and go through it step by step by step. But he does problems, right? And it can be very instructional to hear another person explaining the topic with the same point of view, right? But with different examples and having a different way of saying it. So if you are confused about something coming up, especially now that we're in chapter 4, for chapter 4 and 5 and 6 and 7, be sure to look at the video I suggest, because it might help you to hear it from another person that has the same point of view, okay, about the subject. Okay, so finite dimensional vector spaces. Finite dimensional vector spaces are spaces that are the span of a finite number of canonical vectors, or a finite number of vectors. If it takes more than a finite number of vectors to span the entire vector space, it's an infinite dimensional vector space. Finite dimensional vector spaces are vector spaces like Rn and Pn, the vector space of polynomials of degree less than n. Okay, some textbooks refer to Pn as the vector space of all polynomials of degree less than or equal to n, which is silly because that's an n plus 1 dimensional vector space. Why would you call an n plus 1 dimensional vector space Pn? right? It should be less than n so that it had the same dimension as the number that's in the subscript, right? There's nothing we can do about that. I will always refer to Pn as the n-dimensional vector space of polynomials of degree less than n. And the reason this is of degree n is because you need a constant term, right? You need the an at the end for the constant term. So it's an n-dimensional vector space. But notice that we could represent all of these vectors using canonical basis vectors from Rn. For example, we could let x to the n minus 1 power be represented by E1, 1, 0, 0, 0, 0, 0, 0, right? So for example, in P3, the set of quadratic polynomials and lines and constants, right? Then we could use I hat, j hat, and k hat. And I hat would be x squared, and j hat would be x, and k hat would be 1. There is a deep relationship between the list of numbers from a1 to an and the list of coefficients that make up the polynomial p. Whenever we have a relationship like that, we refer to it as an isomorphism. And we're going to learn in Chapter 5 about linear transformations. An isomorphism is a linear transformation that also happens to be a bijection. A bijection means one-to-one and onto, which is something you were supposed to have studied in the past, right? Functions always map every single element of the domain to exactly one element of the codomain, right? But one-to-one functions map exactly one element of the codomain to only one element in the domain. And onto functions use up all of the elements, of the codomain, right? So one-to-one and onto means the sets are exactly the same size, and the map maps exactly one element from one of them to exactly one element of the other one. So that they're essentially very similar. And if you have a linear transformation that happens to be this bijection, they're not just similar, they're algebraically exactly the same. As far as algebra is concerned, there's no difference. So we refer to them as isomorphic. And the linear transformation that's the bijection between them is called an isomorphism. And the isomorphism here is the one that lists all of the coefficients from the leading coefficient to the constant term in a list. And that gives you, for every single polynomial of degree less than n, a vector in Rn, and for every vector in Rn, exactly one polynomial of degree less than n, an isomorphism. So if we are using MATLAB or Fluent or Fortran, right, or C++, how do we represent 3x squared minus 5x plus 4? We just use the vector 3, negative 5, 4, right? 3x squared minus 5x plus 4. Where instead of I hat, j hat, and k hat, the canonical vectors are x squared, x, and 1, right? Does this make sense? And so there is this isomorphism, capital Phi, that maps 3x squared minus 5x plus 4 to the column vector 3, negative 5, 4. And it's invertible, so its inverse would map the vector 3, negative 5, 4 to the polynomial 3x squared minus 5x plus 4. And so we say that these two representations, these two elements of two different vector spaces, are isomorphic to each other. And we use that equivalent, which is the equal sign with the tilde over the top of it. Sometimes back in geometry class in high school, we called it conjugate, right? Conjugate to. And we mean the same thing. Okay. So, let's look at some spans. For example, what is the span of I hat and j hat in R3? You have to read the questions really carefully. Because when you saw I hat and j hat, you were probably thinking R2, because you only saw no k was listed anywhere in sight. But in this case, no, we mean I hat and j hat in R3. So in this case, I hat is the vector 1, 0, 0. And j hat we mean the vector 0, 1, 0. And what is the span of these two vectors? The ghost in the machine. Okay. What is the span of these two vectors? Well, it would be the set S, let's for span of I hat and j hat, would be the set of all vectors, A times I hat, 1, 0, 0, plus B times 0, 1, 0, such that A and B were any possible real number. And we could describe it as the set of all vectors A, B, 0, where A and B were real numbers. You see how this works? Sort of familiar to what we had been doing. It follows that pattern where the first coordinate's one thing, the second coordinate is another thing. How do we know that they're linearly independent? By linearly independent, for two vectors, we mean they're not linear, they're not multiples of each other. They don't lie on the same line. But we also need to talk about linear independence for larger groups of vectors. All right. So in this case, we just mean the second vector is not a scalar multiple of the other vector. Okay. If we subtract the other vector from both sides, it looks like this. And that looks a lot like a linear combination, a linear equation. Because -1 could be just another constant. So now we're going to call them, you got to change when I click you, C1 and C2. And we could write this in matrix form. No, you have to click. Okay. What we're really asking is there some linear combination of these two vectors that gives us the 0 vector? Well, sure, if C1 and C2 are both 0. So again, we're not asking, is there some linear combination of these two vectors that gives us a 0? Is there another linear combination of these two vectors that gives us the 0 vector, besides just 0, 0? Well, wait a minute. We've had that sort of question before. AX equals 0 always has one solution. That's where C1, C2, the vector x, is the 0 vector. Thank you. The question is, does it have more? And if it is even one more, it has infinitely many, right? So we're asking ourselves, what is the null space of A? The set of all of the vectors in the domain, in this case R2, since we only have two vectors, such that AX equals 0 in R3. And if it's trivial, if it has only the 0 as a solution, then we say, well, these two vectors are not multiples of each other. They're linearly independent. But if there is some other linear combination, there will be infinitely many, and that null space will have an infinitely many vectors in it. And A will be a non-singular matrix, right? Well, it's not square, so it can't call it non-singular or singular. But both of the columns won't be pivot columns. One of them will be a free column. Okay. So in R3, the span of 1, 0, 0 and 0, 1, 0 is a plane, right? It's the XY plane. And it passes through the origin, so it's a subspace. What is the span of I hat, j hat, and I hat plus j hat? Well, I hat plus j hat, isn't that a linear combination of I hat and j hat? So it was on the same plane as the span of I and j in the first place. The span of I hat and j hat is the xy plane. But the span of I hat, j hat, and I hat plus j hat, well, I hat plus j hat didn't add anything new. If we drew a picture, we'd have I hat, go the other way, j hat, and I hat plus j hat, right? They're all on the xy plane. So one way of defining two vectors as being linearly dependent is that the span of ij and I hat plus j hat is just the span of I and j. The I hat plus j hat didn't add anything new. So this set of vectors is said to be linearly dependent. And they're linearly dependent because the span of all three of them is equal to the span of a smaller number of them. At least one of the vectors was irrelevant. Now, how do we compute that? How are we going to do that in our homework problems? Well, let's form a matrix that has I hat, j hat, and I hat plus j hat. Right? Isn't this the correct matrix? Is this matrix already in reduced row echelon form? Yeah. And doesn't it have a free column? And isn't the third column 1 times the first column plus 1 times the second column? Okay, so because I have a free column, yeah, what are you going to ask? Was somebody going to ask a question? Okay. Because I have a free column, I know that one of the vectors, at least one of the vectors, is a linear combination of the others. In fact, the third one is the first one plus the second one, right? So they're linearly dependent. So there is a difference between the idea of linearly dependence, which is that the span of the three vectors was actually equal to the span of a smaller number of them. Algebraically, how that comes into play is that is the matrix formed AX equals 0 have more than one solution, infinitely many, or just the one solution X equals 0. But the actual definition, the way that mathematicians write it is, we look at the linear combination C1 times the first vector plus C2 times the second vector plus C3 times the third vector and if this algebra problem has a non-trivial, non-zero solution, right? then it has infinitely many non-zero solutions, and one of those vectors is a linear combination of the other. And the way that works is, if it has a non-trivial solution, at least one of those C's is not equal to 0, right? So we can subtract it from both sides. And we get something that looks like this. And then we can divide both sides by C minus C3. And that makes the equation look like this. And see, the third one, 1, 1, 0, is a linear combination of the other two. In this case, C1 is 1 and C3 is negative 1, and C2 is 1. But aren't there infinite limited possibilities? Just as long as C1 over C3 and C2 over C3 turn out to be 1s? Okay. One vector is a linear combination of the others. And the way that we recognize that is we form a matrix that has as its columns all of the vectors that we were asked to determine whether or not they were linearly independent or linearly dependent. And we reduce that matrix. And if we find a free column, then we know they're linearly dependent. And if that matrix turns out to have no free columns at all, so it's square and it's row equivalent to the identity, then they're linearly independent. Okay? So the definition and how we do it are a little different. But the definition is one vector a linear combination of the others. In other words, does this problem have more than one solution or a non-trivial solution? Is the one that works even if we have an infinite dimensional vector space or one of these abstract vector spaces like the vector space of all functions with two continuous derivatives, which turns out to be super important in STEM. Most of our mathematical models in STEM are either a differential equation of second order because you have acceleration and velocity, or if you're doing fluid dynamics, third order because you also have jerk, right? You have the instantaneous rate of change of acceleration, right? Or it's statistics, but statistics is something else. Right? These second order differential equations need a solution that has two continuous derivatives. Right? So the vector space of functions with two continuous derivatives turns out to be super important. The unfortunate part about that is that it's infinite dimensional. So what are we going to do? And that's what we have to talk about in chapter 6 and 7. What are we going to do? We're dealing with an infinite dimensional vector space. The other unfortunate part about that is we're computing derivatives, right? And integrals. So let's ask ourselves, if derivative is a linear transformation from the vector space of functions with two continuous derivatives, and it gives us its derivative, what is the kernel? Oops, did I forget the n in kernel? Of D. The kernel in D is the set of all functions f such that d of f equals 0. Ooh. How many functions have a derivative that's equal to 0? Everywhere. All the constant functions? Isn't that infinitely many?
Yes.
So D is a singular, right? Linear transformation. It's not even non-singular. And has anybody currently enrolled in or has taken differential equations yet? Do you ever get one solution or do you always get infinitely many? Right. right? The null space. We're going to find out later we're getting the null space, the kernel. You solve the homogeneous system. Right-hand side 0, that's the null space, right? Same thing. So we have two problems. The vector space we would like to use the most on our computer is an infinite dimensional vector space. And that's going to cause us some problems that we need to discuss in chapter 5 and 6 and 7. And the linear transformation we use the most for velocity and acceleration is the derivative. And it's not even non-singular, right? So it complicates things, right? What about the span of I hat, j hat, and k hat in R3? Are I hat, j hat, and k hat linearly independent? Yeah? Okay. And so their span will be a three-dimensional subspace of R3, but R3 is a three-dimensional vector space. So that must be all of it. That's the other thing you have to think about. If I'm in a three-dimensional vector space and I'm asking myself, what's the span of 6 vectors? Well, it's less than or equal to 3. So those vectors are linearly dependent, right? 3 of them, at least 3 of them are irrelevant to the span. They're linear combinations of the others. And if I'm in a three-dimensional vector space, but I only have 2 vectors, like I hat and j hat, their span can't possibly be all of R3, because the most that they can span is a 2-dimensional subspace, right? Does this make sense? Those are true-false questions on the exam and the final. Can the span of I hat and j hat be all of R3? No, because you don't have enough vectors, right? Can I hat, j hat, k hat, and I plus j, 4 vectors, be linearly independent in R3? No, because you have too many. The largest number of spanning vectors you can have is 3. Of linearly independent vectors you can have is 3. So what about these 4 vectors? Are they linearly independent? And how do you answer that question? Right? And this becomes an important question. If I have a mathematical model and there are 4 polynomials, are these 4 polynomials linearly independent? How could I tell if x to the cubed minus 3x squared plus 2x, 2x cubed plus 2x squared minus 4x minus 3, minus 5x squared plus 2x minus 1, and minus 7x cubed plus 4x plus 5. How do I know if they're linearly independent or not?
You can make a matrix and see if all of it is there.
Yeah, we go back to chapter 1, right? We create a matrix using our isomorphism. And then we go back to chapter 1 and 2. You see why I'm not too worried about the first test? Because we're going to use that sentence, create a matrix, and reduce it every chapter. Every single chapter, we're going to say the same thing. All right? But of course, we're going to interpret the result differently. In this case, we're not going to interpret the result as trying to solve ax equal b. We're going to interpret the result as determining whether or not there's a free column at all to find out whether or not the vectors are linearly independent or linearly dependent. And here it is all. You don't have to write all these steps. You can go straight to the matrix here and then start reducing it. And since the right-hand side is 0, it's homogeneous, I'm not going to put the bar 0, 0, 0, 0. I'm just going to have the matrix A there. And we're going to perform some row operations. And you know, we've got it in reduced row echelon form, but couldn't you have figured out by the time you got to here, this step, that you had a free column? As soon as you know you have a free column, they're linearly dependent. As soon as you know that all of the columns are pivot columns, you know they're linearly independent. Wow, my tongue didn't help with that one. Linearly independent. But things get more difficult with an infinite dimensional vector space. The vector space of all functions within continuous derivatives on the real line. Polynomials have incontinuous derivatives. A polynomial of degree 3 has 12 derivatives, and they're all continuous. It's just that After the third derivative, you're differentiating 0, and you get 0 every time. Okay. But what about sine and cosine, and e to the kx, and absolute value, and e to the minus x squared, and x squared over 2? How do we determine whether these are linearly independent or linearly dependent? And I think we've had 2 people who've already taken DiffyQ or are currently enrolled in it. Okay, maybe 3 or 4. Do you remember the Wronskian? So we're going to do the Wronskian. We're going to compute the Wronskian. Why does that work? The question we want to ask ourselves is, let's use the definition of linearly independent. Is there some linear combination of our n functions that gives us 0? Right? Is there some linear combination of them that gives us 0? Well, what if I compute the derivative of both sides? Isn't the derivative of the sum of the derivatives? And the derivative of c1 times f1 is c1 times f1 prime? And isn't the derivative of 0, 0? I mean, that 0 on the right-hand side is not the number 0. It's the function 0 whose graph is the horizontal line with slope 0 and y-intercept 0. This room has electrical problems. Okay. Either that or a poltergeist, but I don't believe in those. Okay. So, what if I differentiate both sides n minus 1 times? Don't I get n equations and n unknowns? The unknowns are the c's. So I get this. And that's a square matrix. And if its determinant is equal to 0, right, then it's singular, and I know that they're linearly dependent. But the things I'm computing the determinant of are functions. So this is what you got to be careful of. If the determinant is always 0, then they're linearly dependent. But if the determinant is not 0 for even 1x, then they're linearly independent. And by the way, that x has to be between a and b, right? It has to be at least a and no bigger than b. But of course, if we use up, like we did up here, minus infinity of infinity, then x can be any real number. And the Wronskian is the determinant of this n by n matrix full of derivatives. So, for example, how do we know that sine of one integer m times x is linearly independent from cosine of m times x? Well, we would we've got 2 functions, we need a 2 by 2 matrix, right? So we would differentiate sine mx and get minus m cosine mx, or plus m cosine mx, and we would differentiate cosine and get minus m sine mx, and then we would compute the determinant, and we would get minus m times sine squared minus m times cosine squared. We could factor out the minus m and get sine squared plus cosine squared, which is 1, and then we would get minus m. Presumably, we never chose our integer to be 0 because that would be a waste of time. Cosine of 0 is 1 and sine of 0 is 0. Okay? So as long as that m was not equal to 0, then they are linearly independent. This, as we're going to see in this chapter and in chapter 5, turns out to be super important. That cosine of 3x and sine 3x are linearly independent. It is used in electrical engineering and physics everywhere. All over the place, in your phone. There are probably 5 different processors in our phones, all using the fact that sine 3x and cosine 3x are linearly independent. And I'll explain in chapter 5, okay? Or chapter 6. Chapter 6. But one of the homework problems you have is, this is part of that homework problem. Now, how do we show that cosine of m times x and cosine of n times x, where m and n are different integers, positive integers, are they linearly independent? if m and n are different, meaning they're not equal, I could have used the fancy word distinct. You'll see that one in the homework a lot and on the test questions. Distinct, which is just another fancy word for different, right? Positive integers. Then cosine of m times x and sine of n times x are linearly independent. And if this works for cosine, I assume that you can use something really similar and figure this same thing out for sine. Well, we're going to have to form our Wronskian matrix. So we're going to have cosine of m times x in the first row and cosine of n times x in the second row. And minus m times sine of m times x in the second row, and minus n times sine of nx. And we're going to compute the determinant. And what are we going to get? We're going to get minus n times cosine of mx and sine of nx plus m times cosine of nx. Whoops. We're going to have to move everything over. Create enough space. Times sine of m times x. Drat. What are we going to do? Anybody have any idea?
Probably some idea to be that I've long since forgotten.
The product of sum formula? Okay, I've forgotten the product of sum formula. I can look it up, or if I'm on a quiz or an exam, I may have to figure it out. How do you figure out the product of sum formula?
You ask the professor.
Yeah, that's true. You can ask the professor, but if it's a test, I'm not going to answer. I'm going to say, you got to figure that out on your own. Okay, so I remember two formulas. Those formulas are this one, sine squared t plus cosine squared t. That's just because I didn't want to write thetas equal 1, right? This is the Pythagorean one. And I can divide both sides by sine squared or divide both sides by cosine squared and get the other two versions of the Pythagorean identity. 1 plus tangent squared, or 1 plus cosecant squared, 1 plus cotangent squared, or 1 plus tangent squared, right? I can get any of those three. How does this help me? Well, there's another formula you may not be familiar with yet that it turns out to be super important. And it's if you haven't had hadn't had differential equations yet, it's going to come up. This one does something pretty interesting. It says e to the I theta is cosine theta. This is Euler's identity plus I sine theta. Isn't it weird that it would work out that way? And you can Google this one. Euler figured this out using the Taylor series for e to the x and cosine x and sine x. But that means that e to the minus I theta is cosine minus theta, but cosine minus theta is cosine theta, plus I sine minus theta, but sine of minus theta is minus sine theta. If I add these together, I get e to the I theta plus e to the minus I theta equals 2 times cosine theta, because the I sine thetas add out to 0. So the actual mathematical, for math major, definition of cosine is e to the I theta plus e to the minus I theta over 2. And if we subtract these two, then e to the I theta minus e to the minus I theta will give me 2 times I times cosine, so I'll divide by 2 times I, and I'll get sine theta. Now this is really bizarre, because aren't cosine theta and sine theta real numbers for all real numbers theta? But if you plug i's in for e to the I theta, e to the minus I theta, over 2I, you get a real number. Okay, and it is largely because of this right here that anytime we have wave phenomenon, so if we're in fields and waves or in electrical engineering class, what is impedance? More importantly, what kind of number is impedance? Any electrical engineers?
Complex.
It's a complex number. Yeah. It's a complex number. Impedance, yeah.
So maybe a little off topic, but so Euler discovered, did everything just line up, or Euler happened to be born at the right time to find all of this, or was just one of the
Euler was really smart too.
Okay.
Okay. There are a couple of people in around his time, and the other one was a doctor. His name escapes me because I'm thinking about math, not about biology. Okay. And my mind isn't as quick as it used to be. There we go. It wasn't that quick to begin with. Oh, wait a minute. I'm erasing stuff I want to keep. Okay. Louis Pasteur.
Okay. Pasteurization.
Not just pasteurization, he also discovered polymerization, and he cured rabies, which had no cure before him. And anybody had rabies or know somebody who had rabies? The cure for rabies is very bizarre. You have to have a series of injections directly into your stomach. And by the way, he got it right the first time. He didn't experiment. Louis Pasteur was a scientist, but in the height of French science, as was Euler. So this was a couple hundred years ago. And even science back then was we're still talking about Paris, a very social network of people. So as it turns out, he was very surprised to have the attentions of a very highly placed in social circles woman when he was a young man, who he eventually married. But she mostly married him because he was a famous scientist. But she quickly found out that being married to a famous scientist was boring because he never wanted to go out, right? No socializing. He surprised his wife, who also was a very, very intelligent, college-educated person at the time, with asking her if she wanted to go to some function okay? And before he left, he took one of his own hairs and placed it in a petri dish. And when they got back, polymerization had started, and he was able from that experiment to reproduce it and discover how creating long chains of polymers or plastics, right, was possible. Now, he did this in the open air. And if you know anything about chemical engineering, plastics are not easy to make. It requires very specific temperature, humidity, and barometric pressure, as well as the right chemicals. It's very difficult to seed the polymerization, okay, or to keep it going for long periods of time to create polymers that are long enough to create plastics that we use today. Okay, so the other thing that the French were doing in the 1800s and 1700s is they had already begun measuring rainfall, barometric pressure, temperature, and using balloons to measure it at different levels of the atmosphere. And they meticulously wrote all this information down and kept this information for posterity. Since we have that information, we know that there were only 2 nights in his entire lifetime in which he could have set the petri dish on the windowsill and had polymerization occur because it was the right temperature, humidity, and barometric pressure. And he picked it. Okay. So Asimov, do you everybody know who Isaac Asimov is? Science fiction writer, very famous. Actually didn't write, he wrote over 400 books, but most of them were textbooks. Only a few of them were science fiction. And he wrote a book about Louis Pasteur. And he concluded, so he did a lot of things where he only tried it once and he got it exactly right the first time. And so Asimov was writing there and he says, so how did this man do that? Was he extremely lucky? Was he just the most intelligent person that ever lived? Did God just tell him the answers so that he knew them ahead of time? Or was he a time traveler and he came back in time so that we would survive some apocalypse by creating pasteurization and polymerization? Or was he really from another planet? And Einstein concluded that all 5 of those were equally likely. Because he really did come up with a lot of stuff. Euler was the same way. When Euler was 10, in order to get him to shut up and go away, his teacher told him, come up with a formula to add up the first 100 integers. It took almost 4 seconds. You guys have seen this formula that the sum from k equal 1 to n of k is n times n plus 1 over 2? Like I said, he was 10 and he came up with this formula in just a few seconds. He said, well, 100 plus 1 is 101, and 99 plus 2 is 101, and 98 plus 3 is 101, so it must be 50 plus 51 over 2. Done. Obviously. Yeah, his teacher was also annoyed. Okay, so yes, he came up with this one. As a matter of fact, there's another mathematician that's going to come up his name in this class several times. Gauss, right? Gaussian elimination. If we had named everything that Gauss and Euler published first after Gauss and Euler, everything in this class would be named after Gauss and Euler. So, mathematicians in Europe decided a couple of hundred years ago to name a lot of stuff after the second person to publish it, so that not everything would be named. Because if everything was Euler's formula, which formula would you be talking about when you said it? And there's Euler's formula, Euler's equation, Euler's identity, right? There are a lot of those. There are Euler's formula for this as opposed to Euler's formula for that, right? It's a lot of stuff. Okay. So, how do we tell if they're linearly independent? How do we figure out all of our trig identities if we forgot them and we only know 2? The Pythagorean identity and Euler's identity. These are the only ones that we've got. Well, the sine of u plus v plus cosine. The cosine of an angle, even if it's u plus v, plus I times the sine of an angle, even if it's u plus v, is, according to the only other formula we memorized, e to the I u plus v. But when we're adding exponents, what are we really doing? Multiplying, right? So we get e to the iu, e to the iv. Wait a minute. E to the iu is cosine u plus I sine u, and e to the iv is cosine v plus I sine v. And now we can just FOIL it, right? So we get cosine u cosine v plus I squared, that's a minus 1, because I squared is negative 1, times sine u sine v plus I times sine u cosine v plus cosine u sine v. So the cosine of u plus v must be cosine cosine minus sine sine, and the sine of u plus v must be sine cosine plus cosine sine. So what is cosine of 2t? Well, it's cosine of t plus t, which is cosine t times cosine t minus sine t times sine t. But we can replace sine squared with 1 minus cosine squared. So you get 2 cosine squared minus 1. And cosine squared is 1 minus sine squared from the Pythagorean identity, so we get 1 minus 2 sine squared. If we solve this one for cosine squared, we get the power reduction formula, cosine squared, equal, because I have the 2, I'm going to have to multiply by 2, 1 plus cosine 2t. And if I solve this one for sine squared, then I'm going to have 1 minus cosine 2t. Now I have to ask myself, I've got cosine times sine. Which one of these has cosine times sine in it? This one. Come on, move. Sine of u plus v is sine u cosine v plus cosine u sine v. By the way, what's the other way to remember that this identity? The mnemonic expression is sine keeps the sign. Sine puts sine here first, and the sine of u plus v keeps the plus sign. So sine keeps the sign, both sine and sign. And cosine does the opposite. So it'll be cosine cosine minus sine sine. Okay, enough of that. Sine of u minus v is going to be sine u. Cosine v, because the cosine of negative v is the cosine of v, minus cosine u. And sine v, because the sine of negative v is minus the sine of v. And if we add these together, we get sine of u plus v plus sine of u minus v equals 2 sine u cosine v. I'm not going to ask you to do this on an exam. That's okay. But you should know how to come up with them on your own. There's a straightforward way to get all of the trig identities you need, and this is the way to do it. I can get any product to sum formula or sum to product formula if I just start with the Pythagorean identity and the Euler's identity and just derive it. And this is the way I do it. I don't memorize these, I just derive them because it's too much work for me to have to memorize them. So sine u times cosine v is 1/2 of sine u plus v plus sine u minus v. Isn't that what we need? We're good for time. We're doing all right. Even though we stopped to talk about Pascal, Louis Pascal. Louis Pascal was just amazing. And so were a lot of his contemporaries, like Euler. Okay, so if we need to replace this cosine. We have sine n, cosine m. So we have sine, we have an nx here, and we have an mx here. So we're going to get 1/2. I'm going to put that 1/2 outside. Nx mx. So what do we got? We've got sine of mx plus nx plus sine of, let's see, nx minus nm minus mx plus m over 2. And we're going to get, now they've switched. Sine has the m, and cosine has the n. And we're going to get, come on, sine of mx plus nx plus sine of, okay. And this is going to give us u mx minus nx. That looks more complicated, but it's not. Minus n over 2 sine m plus n x plus sine n minus m x plus m over 2 sine m plus n x plus sine. Now, minus sine, because I'm switching the m's and n's, m minus n x. Now, why did I do that? Well, these two already line up. I just wanted to make the other two line up. Oh, if I switch them, it'll be n minus n, right? And now these two will line up. So what do I end up with? Minus n over 2 plus m over 2 times sine m plus n x plus minus n over 2 plus m over 2. Well, wait a minute. We have this minus sign here. So we have n over 2 minus m over 2 sine n minus m x. And what we're really trying to ask ourselves is, can this ever be equal to 0? Well, what do I know about this m minus n here? I know it's never equal to what? Since m is never equal to n, m minus n is never equal to 0. So I don't have a 0 here, and I don't have a 0 here. And the question is, can this ever equal to 0? And if m and n are integers, aren't n plus n and n minus m integers too? Okay. Okay. Equal to 0. All right. There were a couple of things that we could have done, but I wanted to do trig identities because they're going to come up again. And you needed to know how to dig through them. You needed to remember. Is this, some of this sort of coming back to you? Some of it? Not all of it? Some of it? Okay. We'll save it. All right. We could have done the same thing back here, but I wanted to show off trig identities. Is there a single x when this is not equal to 0? How about x equal pi over 4 Now see, it wasn't as easy to see here, but it's much easier to see here. Because m plus n is just an integer, right? And m minus n is just an integer. Did I get the minus signs right? Did I make a minus sign mistake somewhere? I don't think so. All right.
Looks right.
Yeah. All right. So what if m plus n times x was equal to pi over 4? So x was equal to pi over 4 times m plus n. Well, then what would this be? Remember the 45, 45, 90 triangle? Pi over 4. If this is equilateral, then the sine and cosine are both 1 over the square root of 2, right? The question is, okay, what's the relationship between this one and this one? So, geez. If m plus n over times what? This is pi over 4 m plus n. Gives me my nice pi over 4. Now we know what x is. It's pi over, what's n minus m times pi over 4 times m plus n. I'm not sure why I'm going down this rabbit hole. But it's pi over 4.
Is that n minus m times pi over or equals?
Okay, so all I know is that m and n are integers and that the numerator is not equal to 0. The question is this going to give me a sign that's equal to 0? When is sign equal to 0?
0 or 5 or a multiple of that.
That's right. It's x has to be a multiple of pi for some integer, even negative integers. There. So, what we really need to know is 1/4 of n minus m over m plus n equal to some integer. Well, that would mean that n minus m over n plus m had to be 4 times an integer. And can that even happen? There is an easier way to do this. But I trust my math steps. When I make a math step, I trust it. Let's see here. This is the right identity, and it does get you here. Did I differentiate correctly? Yeah. Okay. No, all of this is correct, but it's sometimes you do all the right steps, but it makes it harder instead of easier. That's what I forgot. So this looks really horrible, right? It does. It looks really horrible. I don't know about you, but it looks really horrible. So what do we do? So where do we go from here? Well, we've learned about vector spaces, and we're going to learn more about vector spaces in Chapter 4. But in Chapter 5, I'm going to bring up something completely different. I'm going to talk about linear transformations, and that's not going to seem like such a great topic either. That's going to seem very abstract, just like this chapter does. And eventually we're going to talk about dot product, right? Now, in this class, every dot product is an inner product, but not every inner product is a dot product. So we're going to have to handle what does it mean to be dot product in an abstract vector space, right? We have to extend our understanding some more. And the hardest part about this class is it's hard to get through chapters 4 and 5 because they seem so abstract. But when we get to chapter 6, we're going to come back to solving lots of problems, lots and lots of 20th century problems. And let's see. X dot y is the length of x times the length of y times the cosine of the angle between them, right? And x dot x is the length of x times the length of y times the cosine of 0, because the angle between x and x is 0. Oh, length of x times the length of x times the cosine of 0, which is its length squared. And we're going to realize that if we have dot product, then we have length and angles. We'll call the length of a vector the square root of the dot product of the vector with itself. Yeah, I know what time it is. And we're going to call the cosine of an angle the dot product between the two vectors divided by their lengths. So this is a great thing. To a mathematician, it says, oh, I only have to define one thing, dot product. And if I define dot product, I get length and angles. So I'll have all this linear algebra that we studied in the first 5 chapters, and I'll have length and direction, length and angle, direction, and I got that from just defining dot product or inner product. So the question is, what do inner products look like on these abstract vector spaces? What does it look like in Rn? Well, you multiply the first coordinates, and you multiply the second coordinates, and you multiply the third coordinates, and you do that for all the coordinates, and then you add them all up, right? This is dot product. You're familiar with this? This is dot product. Well, you multiply all of the coordinates together for every x, and you add them all up.
That's x dot y, right?
And this is the dot product. And we're going to use a different notation because it's an abstract vector space. We're not going to write f dot g. We're just going to write, you're going to use angle brackets. And this is the inner product. Well, what's the inner product of cosine m times x and sine cosine n times x? Well, integral. We're going to go from, we're going to add a 1 over pi and go from 0 to 2 pi. So we're in the vector space C2 of 0 to pi. So we'll get 1 over pi times the integral from 0 to 2 pi of cosine mx times cosine nx dx. And remember, I told you, every one of your phones has 4 or 5 processors on it, all using this identity. So it's going to be super important. And this is why I brought up all this trig stuff, right? I had a moment to talk about something else besides just what's going to be on the homework next week. And so I took this moment to remind you about trig. All right? And, ooh, how do we integrate this one? We're going to have to use the product to sum formula. Okay. Cosine, yes. This is the product of sum formula for cosine as opposed to sine. And let's see, we're going to get 1 over 2 pi. And what's the antiderivative of cosine kx? Isn't it 1 over k times sine kx? Or sine kx over k? And what's the antiderivative of cosine kx again? And remember, m and n are integers, and they're different integers. So m minus n is not 0, but it is an integer. So what is the sine of 2 times n plus n times pi? Yeah, isn't that an integer multiple of pi? So I get what? 0. And the sine of m minus n times 2 times pi? And the sine of 0? Wait, what does it mean for the dot product to be equal to 0? They're perpendicular. Wait a minute, if they're perpendicular, can they be linearly dependent? No, they're perpendicular. Of course, in an abstract vector space, we're going to say cosine mx and cosine nx are orthogonal. So all perpendicular vectors are orthogonal, but not all orthogonal vectors are called perpendicular because they're from an abstract vector space. Okay, so we have a couple of chapters of definitions and things mathematicians live for, but stuff that people aren't mathematicians usually find pretty boring and dry. But we need chapter 4 and chapter 5 to do chapter 6 and chapter 7. Chapter 6 and chapter 7 is going to seem, if you've had any upper level STEM courses at all, oh my goodness, that's why we did that, right? So you got to stick with me with this definition of subspace and linear independence and linearly dependent and span, right? And dimension. And get through this chapter and get through chapter 5 on linear transformations, because there is this huge payoff at the end for going to all the work to create your understanding of those two abstract things. Okay? Linear transformation and vector space and subspace. And I know that they seem pretty bizarre right now, but they're not going to seem so bizarre in chapter 6. And they're going to allow us to solve all kinds of problems that some of you have already been taught how to solve. You just were told, you realize you're using linear algebra, right? Okay, so I'll see everybody on Monday. We've just got homework due, and we've got the discussion board to talk about all the stuff that we're working on. And and I'll assign a written assignment from chapter 4. If we look at that, do you want to look at it really quick, or do you need to get out of here? Okay. Remember, these are the projects, right? So if we go to course materials and access WebAssign and pull up the ebook for linear algebra and not calculus. And of course, it's not going to answer. Yeah. 511. And go to chapter 4. Come on. You have a gigabit Ethernet. We can't possibly be fast. Oh, yeah, that's another thorn in my side. So what you're going to be doing is you're going to look at solutions to linear systems, right? And ask yourself, okay, if I know the solution to AX equals 0, does that mean I know a lot about the solutions to AX equal B when B is not equal to 0? And the answer is yes. If I can solve AX equal B1 and AX equal B2, does that mean I can solve AX equal B1 plus B2? Why or why not? Okay. And we're going to start with an example. And remember, there's an invisible vertical bar between the vector 3, 1, 0 and the 3 by 3 matrix, and an invisible vertical bar between the vector negative 9, negative 3, 0, and the matrix, the same matrix A on the left. So don't forget about the invisible vertical bar there. I don't know why the author did that. See the equal sign? Whoa, this is a 4 by 3 system. Wait. Oh, but that's a different problem. This is not the same one from problem number 3, okay? So, all of these 5 questions are asking you questions about algebra. They're algebra questions. And you probably know the answers, but if you get stuck on how to answer it, just ask and we'll talk about it on the discussion board, okay? In the discussion board. All right, thank you very much. I'll talk to everybody online hopefully, and we'll see each other on Monday.